Hi, welcome to the LNB training course. The objective of this course is to give an overview of what is an LNB, their importance in satellite communications, give you the right tools to select the adequate LNB, and basic troubleshooting. This chapter covers the satellite communication concept as well as microwave signal path in a satellite link. And furthermore, I will talk specifically about one of the main components of a satellite link, the LNB. Different frequency bands, important satellite parameters like GNT and bit error rate will be covered. At the end, different types of LNB and their applications, diagram, and interfaces. LNB function and how it is used in satellite communications. Chapter 1. Let's start with the key advantages of satellite communications. They can be used in places where cabling infrastructure are challenging. This is the situation of rural areas where satellite communications are a very good option, where investment is not as high as implementing ground infrastructure. It is also a good choice as a backup communication system, in case something happens to the primary line of communication. Satellite communications are reliable and offer a wide coverage. They are easily scalable, where adding nodes does not require major change on the network. They are also a good solution for mobile backhauling. Sometimes the implementation of satellite technology and techniques could be more cost-effective than installing cables infrastructure. In most cases, expanding the network might not require changing any hardware. The two main functions of the LNB is to amplify the received signal coming from the satellite, which is attenuated by the atmosphere, and perform a frequency conversion from the satellite band to a generic band that most of the satellite equipment can use, which is the L band. LNBs can work on multiple frequencies. These frequencies in the spectrum have been categorized into bands. The ones used in satellite communications are C-band, X-band, Ka-band, Ku-band, Ka-band, and Q-band. LNBs are installed on what is called Earth stations. The basic function of an Earth station is to transmit and receive signals to and from a satellite. The signal that is transmitted to a satellite is called uplink, and the signal received by an Earth station is called downlink. Here's an illustration of an Earth station and its component. They have two main sections. One is the indoor unit, or IDU, which normally contains modulators, modems, encoders, switches, and routers that can handle digital information. And the second one is the outdoor unit, or ODU, which normally includes antennas, bugs, LNBs, and RF filters, which are associated to analog signals. The connection between the IDU and the ODU is called an interfacility link, or IFL. The system performance on Earth stations can be measured with two main parameters expressed as G over T. A higher G over T indicates better performance from all the Earth station components added up. G is the antenna gain, and T is the equivalent noise temperature of the receiving system, expressed in Kelvin units. Noise temperature will be explained on a later video in this training course. LNB has two impacts on the system performance. First is the system throughput, and the second one is the bit error rate, also expressed as BER, which means there will be a fault, and LNB has two impacts on system performance. First is system throughput, and the second one is bit error rate, abbreviated as BER. The B here means bit or bits will be incorrectly interpreted by the satellite receiver. In other words, once received as zeros and vice versa. System throughput is related to the performance of the whole system, where an LNB has an important impact on it, in particular the noise figure. Noise figure is the measure of degradation of the signal-to-noise ratio caused by the LNB internal components in the signal chain. The higher the noise figure gets, the weaker the system throughput. Therefore, LNB's noise figure is one of the most important factors, which has the most significant impact on the system throughput and the bit error rate. There are three types of LNBs: the arrows, PLLs, and LNBs. The DRO use a dielectric resonator oscillator to generate the local oscillator frequencies necessary to downconvert the satellite signal to the IF band used by satellite receivers. The DRO LNBs are used with large symbol rate signals since the LO stability of the LNB is not that high. On the other hand, PLL LNBs use a digital phase-locked loop circuit to generate the local oscillator frequencies needed to downconvert the satellite signal to the IF band. PLL LNBs are used for narrowband signals since they have a higher LO stability. LNBs are a combination between an LNB and the feed horn. A feed horn is basically a metal funnel that guides the incoming signals to the actual antenna stub inside of the throat of the LNB. LNBs are mostly used on satellite TV applications for commercial homes where manufacturer parts have to be at a low cost. Another classification of the LNBs are by their reference. They can have an internal reference or externally injected. Typically, the reference is a 10 MHz signal that is used to make the down conversion. If the reference is internal, the LNB has internally this reference. The external reference LNB should be provided by an external device such as a satellite modem. Another classification of LNBs are by their reference. They can have an internal reference or externally injected. Typically, the reference is a 10 MHz signal that is used to make the down conversion. If the reference is internal, the LNB has internally this reference in their electronics. The external reference LNB should be provided by the external device that is connected, such as a satellite modem. Now let's talk about how an LNB works. As we have mentioned, the two main functions of the LNB is to amplify and perform a frequency conversion. Inside the LNB, the first signal process is the amplification, normally by the LNA or low noise amplifier. Passing by this block, the signal moves to a mixer and the local oscillator converts the frequency to IF, which is the intermediate frequency. After that, the IF filter will reject undesired frequencies and amplify the IF signal. At the end of the integrator, we'll integrate the signal to send it out to the output of the LNB. There are three interfaces besides the input and the output of the LNB. The first one is the input voltage on the cable connected to the output of the LNB. This is used to power up the LNB and perform their main functions. Second is the 10 MHz reference, which can be supplied in case the LNB uses the external reference to perform a down conversion. The third interface is a 22 kHz tone signal. This tone, in combination with the different input voltages, can be used to select different bands in a multi-band LNB. On the next video, we will discuss the details on different types of LNBs and its specifications.